Why do we care about resonance, the concept of resonance? The answer is because Lewis structures kinda suck. They are both the very best model we have for determining structures, for writing down structures, for thinking about structures as organic chemists, but they also break consistently and in predictable ways. In other words, if you are trying to diagram out a Lewis structure for a molecule that has the wrong kind of system, then it's not going to be as effective as you want to describe the molecule in question. And so Lewis structures are absolutely the most straightforward, user-friendly way of drawing out molecules on paper, but they also are going to break down literally any time you have a pi system involved. So if I were to draw a cyclohexane molecule, one that looks like this, see, there are no extra pi electrons in the system, everything is in the sigma framework. Said another way, single bonds only. So right now, all I've drawn for you in the Lewis structure format, line angle format I should say, is carbon-carbon single bonds, and I haven't drawn out the carbon-hydrogen implicit bonds that are actually properly part of Lewis structures. Well, so when I say Lewis structures, I actually mean line angle structures here, but because that's what they're based on. The line angle structures are based on the Lewis structure. So we have, again, single bonds that you can see, 12 CH bonds that are not drawn, that are implicitly present. And there's no problems. As long as all you have is electrons that exist only in single bonds, then this is not a problem. Lewis structures work great, and everything you write down is exactly the way it looks. This structure and this model are well aligned. The problem comes as soon as you do something like this and talk about a benzene instead of a cyclohexane. Because here's the problem. If you think about the Lewis structure picture that this is showing, what it suggests is that you have a double bond between these two carbons. So you have a double bond between those two carbons and a double bond between those two carbons, and only single bonds at these three. So if I'm going to exaggerate what this is suggesting, you would expect smaller bonds there, longer bonds there, small bond there, long bond there, small bond there, and so on. This would be the bonding picture you would get from this Lewis structure if you were taking it literally and seriously and assuming that this is the only structure describing it. But nature loves symmetry. So the reality of this molecule isn't that, not as drawn. It isn't this, which is implied by that. The reality of nature is that benzene is in fact a totally symmetrical molecule where you don't have strictly alternating double bonds and single bonds. What you have instead is 6 CC bonds that are all the same length, all of which exist somewhere in a nebulous region between a carbon-carbon double bond and a carbon-carbon single bond. It looks like that. It doesn't look like this, and it most certainly does not look like that. Each one of those carbon-carbon bonds is the same length, is the same energy, and so on. So this is the problem. The reality of the molecule, the structure, when we go and we look at it, when we measure its properties and so on, we see that it is purely symmetrical. And yet, Lewis structures don't allow us to draw that. It just doesn't work. So we have to draw this, which implies this. But we also then have to keep in mind that this is not the only way of drawing the molecule. We could instead draw a Lewis structure where what we have done is essentially rotate the double bonds over a little bit. So what I've done there is imply that this double bond has moved there, this double bond has moved there, and this double bond has moved there. In other words, this is the structure that I get. And these two are resonance structures of each other, which is an unfortunate name because it implies something that's not happening. But nevertheless, that's what we call them. And again, you could immediately say, okay, well, these double bonds could all roll back the way they came, and that's how you move between the two structures. But the structure, the actual structure of the molecule, is not given by this one, and it's not given by this one. It's not given by this molecule. It's not given by the corresponding example that I would draw there. It is instead a superposition of both of those structures at the same time. It's the weighted average of both of those at the same time. In other words, the right way to think about the molecule isn't as each individual Lewis structure, it is instead like this. But the problem is that this is not a valid Lewis structure. This is not a valid line angle structure. And yet, this is the reality of the system. So we're trying to represent this, and we have no good way of doing it. Now, Lewis structures work whenever you have single bound structures. They work great. They are the best model we have. They're user-friendly. They're way easier than many other ways of depicting this structure. So we don't want to throw them out. But what we have to do instead is keep in mind that a Lewis structure is going to be not this individual structure, not this individual structure, but is instead going to be the weighted average of both structures together. So we draw one, we imagine the other, and we keep in mind that the reality isn't either one, but the reality is something else. The core of resonance structures is that reality is not given by any single example, and instead reality is the weighted average of all such structures. So because Lewis structures are great for some things, and because they specifically break down when you have pi electrons, what we do instead is draw one picture, keep in mind that we can draw other pictures, and the reality is going to be given by summing up, averaging across all such pictures to give rise to a structure that isn't any one of them, but is instead all of them kind of at the same time. Now, why do we care about resonance structures? Well, fundamentally because the reality of the molecule is not what it would appear to be if you were looking at each individual one. That's the main reason why we care about resonance structures. The way a molecule looks, the way a molecule reacts, is not going to be given by the way you choose to draw it the first time, but instead is going to be given by some kind of average of many different structures that you can draw.
All right, what we're looking at now is Gaussian. This is a chemistry calculation and drawing software. It allows you to manipulate various images. And this has been fed many bits of real data in the past, and so you can build fragments like this benzene molecule with data that's based on real measured values. So, for example, for a carbon-carbon single bond of the sp2 variety, you can see that it is 1.54 angstroms as the standard stored piece of data. By contrast, the carbon-carbon double bond will be 1.355 angstroms. But every single carbon-carbon single bond in the molecule is 1.54 angstroms, and so I'm alternating between 1.54 angstroms for the single bonds and 1.355 angstroms for the double bonds. And so all of the double bonds are the same, all of the single bonds are the same, but they're different from each other, which is what I was drawing on the board. This is exaggerated, of course, on the board relative to what it looks like here on screen, where everything is more similar than not. Having said that, this is the way it is before you'd run the calculation itself. Now, the power of Gaussian is it allows you to minimize the energy of the system, and if you do that, what you see is that every single one of these carbon-carbon bonds is now somewhere between a carbon-carbon single bond and a carbon-carbon double bond. And I mean that because there's a little bit of double sort of dotted lines as well as the single bonds. But also if you go and you measure, what you see is 1.388 angstroms, which is to say rather more similar to the carbon-carbon double bond and substantially shorter than the carbon-carbon single bond. The carbon-carbon single bond was 1.54, carbon-carbon double was 1.355, and now what we have is 1.388. And again, the key feature to recognize is that every single one of these carbon-carbon 1.5 bonds, if you will, is that they are 1.388 angstroms, but they're all the same. This is a symmetrical molecule. So the reality of benzene is going to be symmetry. Now again, these were calculated values. This wasn't actually measured. But if you do any kind of direct measurement, like with X-ray crystallography or any other technique that allows you to measure more directly, you will come up with similar answers. These answers have been checked by actual experiments and they are accurate. We know that benzene is symmetrical. We know that the reality of the molecule is the symmetry that you would get from the resonance hybrid, not from looking at any single Lewis structure. In the upper right-hand corner, what you can now see is an electronic surface of the molecule. In other words, Gaussian can display where the electrons in the molecule are going to be. And I'm rotating it slightly so that you can see the wireframe of the molecule itself, and you can see the bright red area where the greatest electron density is. And directly above the ring and directly below the ring on the other side, even though you can't see it, is another similar red blotch. The greenish and yellowish areas are slightly less electron density, but the most electron density is right smack in the middle. Then the blue areas are areas of relatively little electron density. In other words, the hydrogen atoms is where there's the least amount of electron density in the molecule. Over on the left, what we now have is the lowest energy orbital of the pi system, and what it's showing you is that the electrons can be anywhere above the ring and below the ring. You should imagine benzene as being constructed of 6 consecutive p orbitals that are all overlapping, and so the electron really can be above and below the ring. It cannot be in the plane of the ring. The pi system can't be there because that's where the sigma bonds are, but the electrons are allowed to be immediately above and immediately below the plane of the ring. Now, what this is showing you is that the Gaussian picture of benzene is rather more akin to the resonance hybrid that I drew on the board, the one that has sort of a dotted ring of electrons, as opposed to either of the resonance contributors that suggest isolated single and double bonds. So again, the key feature is that neither of the resonance contributors with the single and double bonds is correct. Instead, you have this ring of electron density where the electrons are allowed to roll freely around the periphery of the ring. But above and below the axis where the C bonds and CH bonds are. And again, the image to focus on here in the electronic surface is the area of electron density is entirely above and below the ring. The hydrogen atoms themselves are relatively light electron density, and all of the electron density is flowing in this cloud above and below the ring. And that's not the image you would get if you are looking at alternating single and double bonds, but it is absolutely the way that this molecule behaves. The benzene and resonance discussion in your textbook is on page 87 or thereabouts. This is from Bruce, who has an image that's very clearly from Gaussian here in D. And what she's really focused on is, again, what I did on the board. The resonance contributors are not real, but they do combine to form a real thing, which is the resonance hybrid, if you kind of average together mentally the two images. And the reason why I'm showing you this is because of this image that she has in her textbook, where she has a unicorn and a dragon, which likewise is fabled mythical creature that does not actually exist. But together, the elements of both of these mythical creatures can be combined into something that actually is real. Though a rhinoceros really doesn't look much like a unicorn or much like a dragon, in some ways it is the superposition of the two images that she has above. And so that's really the right way to think of resonance in general. It's not that you're flipping between images, Lewis structures, it's that the reality of the molecule is going to be something that's not well described by either resonance contributor that you might draw, but is instead better described by the weighted average of the resonance contributors. So you always are trying to come up with the answer that best describes the underlying real animal as opposed to the mythical creatures. Keep in mind that the core problem is that we're trying to describe a rhinoceros, and for whatever reason, the tools we have available to us are limiting. We want to draw Lewis structures because they are relatively straightforward and a useful tool, but that doesn't represent the actual benzene molecule very well. It doesn't represent the reality of the picture. So instead, what we're trying to do is use the unicorn and dragon, neither of which is real, but we're trying to use it to approximate a real thing, which is the rhino. And the problem really is that our tool doesn't allow us to draw a rhino. Now keep in mind, Lewis structures are in fact the best model we have. As soon as I start drawing out MO diagrams for you in some detail, you're going to wish that we stuck purely to Lewis structures and didn't work with anything else. But they are specifically limited when you are trying to describe delocalized pi electrons, so bear that limitation in mind as you work with them.